Okay, guys. So I know not everybody has everything installed. I know it's a really complicated and annoying process. Hopefully, like in the next, I don't know, 6 months or so. I mean, it's already gotten better since it started like a few months ago. It's just eventually it's going to get up to speed. But for the meantime, it's still worth just kind of exploring what is available. Especially if you are already running mixed effects models. So how many people have like run a mixed effects model before? And are using the LME4 package? Has anybody run it using something else?
glmer.
Well, that's the LME4 package.
Okay.
Yeah. So so I'm not going to like spend a lot of time going over the conceptual aspects of a mixed effects model. But if you've run it in R before, then the whole point of this, like everybody getting together and running a bunch of this stuff, is that this glmer2stan package basically allows you to write code like you would in R, but get Bayesian output. So like I think that the big reason that a lot of people don't go for like Bayesian methods is because there's a big learning curve. And obviously like this is a way bigger pain in the ass than opening up SPSS and like clicking a few buttons. So it's still not perfect, but this glmer2stan package kind of lowers the learning curve a little bit to make it at least a little bit more accessible. So my plan for today, let me see if I can make this a little bit bigger. Can everybody kind of see that at least? So basically my plan for today is just introduce Stan, like what it is, the glmer2stan package, then some of the functions that I've made that were available on GitHub, and that are basically just convenience functions for working with glmer2stan output to make it pretty and interpretable. And then if there's time, we can go over ShinyStan, but that's really like just extra, just for exploring. It looks really cool, it's really interactive, and it's a good learning tool, but it's not essential for inference or anything like that. All right, so how many people have run a Bayesian model in anything, not just Stan? So Stan is just another sampling program. So it's similar to JAGs and bugs in that it runs MCMC samples. So you write the code in the code is written in Stan, compiled into C++, and then comes back into R for you to deal with the output. So all the packages and crazy stuff that you're installing is so that R can do that communication, so that you're not actually writing C++ code, you're writing R code and then dealing with just the output part. And then the rstan package that's the R package that interfaces with Stan. So that's what does all the heavy lifting in terms of reading and writing. And the workflow is basically you write the model code is written in Stan as text, then it's compiled, sent off into C++. That's where all the sampling is done. So the MCMC samples from the posterior, then that comes back, and then you summarize those posterior samples in R to do all of your inference and stuff. So as just like a really kind of basic example, I just wanted to demonstrate like a simple bivariate regression. So just one predictor predicting one outcome. And so for the example, we've got two variables, height and earn. I just picked them. They're just names. And they're just random variables. So height is just a random normally distributed variable, and then earn is height plus some noise. So I made them so that they're correlated. And then we're going to put them in a data frame called dat. And then we can look at what their relationship looks like here. So nice little linear relationship. And what we're going to do first is just run the frequentist model, which is using the LM function in R. If you've run any regressions in R, you've probably seen something like this. It's basically just going to find the ordinary least squares fit that defines the slope and intercept of that blue line. And then we're going to do the same thing in Stan and just compare any differences. So here's the LM output. So I just wrapped the LM, the actual linear model, in a summary function to make it a little faster. And so here's the output. So the intercept is right around 0. It's basically saying when height is 0, earn is also like right around 0. So that's the intercept there. And then the slope coefficient basically is saying for every 1 unit increase in height, you get roughly 1 point something increase in earn, which makes sense. That's kind of how we built it. So those are our parameters. So those are the main coefficients that we're getting out of LM, and then we're going to replicate this in Stan. So there's just a couple of annoying facts about Stan that I've learned since I've used it. One is that when we're running stuff in R, especially using the lm function, we can just specify a data frame, which is something that is nice and easy. It makes sense. It's got this like organizational structure. But Stan doesn't deal with data frames. You need to give it a list. And its data frames are kind of like lists, except that they have to have the same number of rows and columns. The list allows you to input vectors, so you have a data vector for earning and then one for height, but then you also have to throw in scalars sometimes. So you have to tell Stan how many observations you have. And in order to do that, you have to pack it all into a list. So it's a little bit weird, but the nice part about glmer2stan is that it will do all that stuff for you. So that's why that's such a powerful package, because you don't have to go through all this extra work. You can write code like you normally would, and it'll do this like taking the data frame and turning it into a list for you. So, but for right now, we're just going to run it at basic Stan. And so we're just going to make a list called earnDat, and this just has the two data vectors called earn and height, and then the scalar for the number of observations. And so down here is the actual Stan code, which looks a lot like JAG's code if you've ever written that. Basically, you declare a data block, which is all the variables. And these are the variables that we just put in our list. So n is the number of observations. That's an integer with a lower bound at 0. Just that's what we're declaring. We're declaring that earn is a vector of length n of 100. And then height is a vector of length 100. And so I didn't write this Stan code, I just copy and pasted it. And the idea is here that you're not going to become experts at writing Stan code, but you'll just know how to read it. And then the key thing is that the whole reason why you want to even mess with it is to mess with priors, because we're running a Bayesian model with one big difference is that we can manipulate the prior probability or prior knowledge of these parameters and look at how that affects our output. So up here, we have the priors for our 3 parameters. So this beta 1 is the intercept coefficient. So normally this is like really diffuse. So basically what we're saying is the probability, our prior knowledge about this intercept parameter is described by a normal distribution with a mean at 0 and a huge standard deviation of 100. So if you can imagine a normal distribution like that, it's like gigantic. It's saying any value from super negative and super huge and negative or super huge and positive, they're all pretty believable. So very diffuse knowledge. And that's the same for our slope coefficient as well as sigma, which is just the error, basically all the noise of these points around the line of best fit. And then the model is just our basic like linear model where earn, our outcome variable, is normally distributed as intercept plus slope times our height vector, and then the error around that is our error parameter. So far, sort of making some sense. So first I'm going to run it with really diffuse priors, and then we'll look at the output, and then we'll make the priors horribly incorrect, and then we'll see how that affects it.
Do you have to specify every prior?
Yes.
Okay.
So that's one of the parts that makes it a pain, but normally, if you don't have any prior knowledge, glmer2stan will default to these diffuse priors of 0 to 100, which makes sense for a regression where you're dealing with beta weights, but depending on what the scale of your data is, a normal distribution of 0 and 100 might be very inappropriate. It could be like not wide enough, or it could be like unnecessarily wide.
Right.
So these are just so that these are just like generally really diffuse, but since you're running this Bayesian model, it's worthwhile to look at your data and think of what's a reasonable prior, not necessarily a strongly informed one, but what would be reasonable estimates for this relationship.
So
Yeah.
then,
Oh yeah, sorry, say that.
so then if you do a multi-level model, they need to like specify out just like a lot more priors then, right?
Yeah. So you'll have to have a prior on every single parameter, but you don't have to have them actually be strongly informed. But if you might run into weird situations if you've specified a diffuse prior, but it's still not it's still improper for the data.
Okay.
So are you setting the priors in the model function?
The priors are defined in the model block.
The model block, yeah.
Yeah. So
And so what is that? 5
I have originally had it set at like 5 and then like 0.001. So it was like a very strong prior. Here, let me just rerun it. I'll run it with diffuse priors first, and then I'll run it with those strong priors, and you'll see the difference. So, okay, so we're going to run through that. So the code is basically just a character string. And then we're going to feed that character string into stan, and it's going to like know how to process that. But in R, it's just letters and stuff. So this is actually the workhorse of everything, this stan function. You give it the code, this earn code is basically just this text file here. This is just text. And then the earn dat, that's our list that we looked at before. And then here are just kind of like super bare minimum parameters for the sampling process. So your warm-up. In the MCMC samplers, usually those early samples are kind of wonky as they are converging to the actual distribution. So those are typically not included in inference and estimation. So we're saying that we're going to take the first 100 steps of those chains and toss them out. Each chain is going to have length 1,000, but we're going to toss out the first 100, so we're really just going to have 900 steps that we're going to keep. And there's going to be 4 chains. So in all these cases, usually more is better, but more is also slower. So you're trying to find the most efficient model. You're trying to find the most efficient parameters to get the inference that you need without necessarily like sacrificing whether or not it's going to converge or not. Yeah.
Is there like a rule of thumb for how many iterations and how many chains you should be doing?
Not really.
Figure that out?
Yeah, there's not like a hard and fast rule, but
it'll depend a bit on your model. Like more complex models usually need more burn-in and more iterations, whereas a really simple model like this probably doesn't need too much.
Yeah, and the most important thing is to explore your output and then figure out if you need to run more steps. Like there's like lots of diagnostics that will tell you if there's really bad autocorrelation or if the chains have failed to converge, and then you can visually inspect it to see if there's some issues, and then you can up the number of steps. I had to do that for like my dissertation study because I was running really complex models with like 30 parameters, so they needed to run with like 5,000 steps, but this will be fine with 1,000.
So can you repeat what the 2 values inside the prior, those parentheses are?
So this is basically a mean and a standard deviation.
Okay.
So it's just defining a probability distribution that also happens to represent your prior beliefs of this parameter. So we'll run it first with really diffuse priors. And you should get something like this if you're able to run it. So it's going to translate the model code into C++, and then it's going to really quickly go through the sampling process. Because stan is usually really fast, which is one of the benefits of it. But it still needs to translate to C++. So this usually takes a while, but then if the model is nice and simple, it'll go through. Yeah, so there you go. That basically took like no time. And this output here is just informing you like where the samplers are at in the process. So this is the 4th chain, and it was starting its warm-up. Then there was like some weird errors. It'll throw that usually early on as the chains are exploring the parameter space. They can do weird stuff, but then they fix themselves. And then it's telling you, okay, so the first 100 steps is now done. Now we're actually in the sampling part, blah, blah, blah. And then you get some time, like that took 1/3 of a second to run for that first chain, or that 4th chain. And
Can you explain the chains again? Sorry.
so basically, the way that the reason that we're talking about like chains and stuff is you have your posterior distribution, which is the results of this like Bayesian updating process where your prior times your likelihood, all that shit ends up in a posterior distribution that's super wonky and crazy and intractable to like define mathematically. So you send out these like sampling chains into the posterior distribution to sample from it, and then the samples themselves are going to describe the actual probability distribution of the parameter without necessarily explicitly defining that distribution, because it's too difficult to, and you can stop me at any time, Jim, I could be totally wrong.
So more chains equals more sampling, so it'll take longer, but it'll be more accurate?
Yeah, because chains can get stuck. Okay. And I mean, you don't need to run like 100 chains unless there's like some special reason, but usually like a couple is better. But it's for the purposes of, again, just being more accurate and allowing them to like properly explore that parameter space.
And in this case, you're only trying to find a posterior of one parameter, right? Earning?
2 parameters, intercept and slope.
Oh,
Right, height, the effect of slope, or the slope parameter of height predicting earning, and then the intercept parameter are both being estimated.
Okay, and so if you had 2 predictors, you'd be predicting 4 posteriors, intercept and slope for each.
Yes, yeah. And then actually there's also a sigma parameter which is also being estimated. So we have 3 parameters in this model.
I see, so 2 per predictor plus 1, because there's only one sigma.
Not necessarily. I mean, a regression has 1 intercept coefficient.
Yeah.
So then you have multiple beta weights. So if we added another predictor, that would just be 1 more parameter that we'd be
So it'd
estimating.
be 3.
Gotcha.
It'd be 4 because we also have a sigma, the
Plus the
noise
sigma.
parameter.
Okay.
Yeah.
So, okay, so going back to chains, that's just pulling from the posterior distribution, sampling from that.
Yeah.
So I guess you can't use calculus over that. Is that why?
That's basically
Define a
why.
function, and
Yeah.
You take a lot of samples to.
Yeah, like if it was just a normal
Sure.
distribution, if it was just like a single normal distribution, that
Yeah.
is easily like mathematically defined. It's like pi, sine, and some
Right.
other nonsense. But when the distribution is like like crazy and like high dimensional, you can't define it mathematically. So the chains go in and they're defined by probability, and they basically the samples begin to represent the actual density of that super confusing distribution that you can't mathematically define.
And then are there more than one posterior distributions that you calculate, like iterations of that, or what are?
There's one posterior, but there are multiple parameters represented. The posterior represents all possible parameter combinations.
Okay.
So just imagine it as this really hyper complex blob of data, and that you're searching through and then telling Stan what things to monitor and look for. Does that make
Yeah.
some sense?
Yeah.
Okay.
So is it the chains that are going through the iterations?
Yes.
Okay.
So so this stuff that you're seeing that's like going from 10 to 100%, that's just the chain completing its steps. And so then we print out our output, and basically this is the inference that we can draw. So if we were going to like, is earn a significant predictor of, or is height a significant predictor of earn? This is what we would use to come to that conclusion. So what we have here are the posterior mean of the samples, which, if you remember from the frequentist model, was like negative 0.02. Here it's like negative 0.03, so probably rounded a little bit. Same for our slope coefficient, 1.18. That's same as the frequentist model. And then the sigma, which is just the noise around around that line. The standard deviation is the standard deviation of those believable parameter estimates. So for each parameter, we had like 3,600 samples because we had 4 chains sampling 900 iterations. So we have 3,600 samples per parameter. And then those samples are summarized. So the mean of those samples is our best estimate. Then the standard deviation is how much variability there is in the believable estimates for that parameter. And then here are just quantiles. So like the 2.5% and 97.5%, that would define the boundaries of your 95% highest density interval. So 95% of the believable values for the intercept of height predicting earn, which is basically this point right here, fall between negative 0.24 and 0.20.
Why are my numbers dramatically different than yours?
Because I changed the prior, so that's what I was going to rerun. How having an improper prior can like totally change this stuff. Yes, so good point. This number of effective samples basically takes into account the fact that there's autocorrelation among the chains. So if the chains are autocorrelated, then even though you're running 3,600 iterations, what you're actually getting out of that can be dramatically less than that. Because you could have a chain that gets stuck and it's just like not sampling anything different, and it won't actually be providing you any more information. So these are diagnostics for figuring out whether or not you need to run more chains or there's some problem in your model.
And because we're doing a bunch of samples, if you rerun it, you'll get something slightly different, right?
Not if you won't. The posterior means and HDIs shouldn't really change. If it's converged properly, there shouldn't be a huge. I mean, it'll be slightly different, but it should be at like a decimal point that is no longer relevant. Like this, you probably wouldn't rerun this and get like 2.6. I mean, you shouldn't unless something was really
mine's
wrong.
pretty different than yours. I mean, intercept's 0.1.
Because of the
Prior.
improper prior. I changed it, so we'll go back to that in a second.
So right now, mine is a random distribution prior, and you have a.
I'll show you exactly what yours
Okay,
is in a
good.
second.
This is just a non-informative prior, so it's like it's flat, whereas the other one is just highly informative.
Was sharply peaked at the wrong value. Yeah.
Okay.
So
Uh,
I changed it to match 0 and 100, so that's what you have, right?
Yeah.
And it came out like this.
It came out like looking like this.
Different than that.
How different?
So 0.1 instead of for beta 1 and 1.02 for beta 2.
Yeah. So something must not. You must not have like.
I might have
Did
missed some
you
other
change
part.
the sigma as well?
Did I have it?
All of them were 0 and 100.
Yeah. I'll rerun it and I'll show you exactly what I did differently. But just last thing, this r hat coefficient is another diagnostic. 1 is the lowest it can be. If it's 1, that means that the chains have probably converged. Again, like you never know for sure. These are just like guesses as it converged. But this is a good estimate. If it's greater than 1.1, then something is probably wrong and you need to run the chain longer or something else is wrong. So
Wait, Christian, stop. Hold on. Before you go to the next thing.
Hmm.
For the NF stuff,
yeah.
big number's good or bad?
Well, if it's closer to 3600, that means that your chains are perfectly uncorrelated with each other, which is good.
Yeah.
Okay, so let's jack up these priors. So let's set the intercept to be, like we know that the intercept is roughly around 100, but let's say we have really strong prior knowledge that it should be around 5, which is going to be somewhere way up here. And we're setting the standard deviation to be super, super tiny. So this is setting the prior to be sharply peaked around 5. And then we can rerun everything. So if you may have gotten some slightly different results, but you have to rerun the model code and then refeed it back into Stan in order for it to know that you made any changes. And then what we can do is we can compare like the output to what the actual data is and what's called the posterior predictive check. So we're going to take the output from Stan and see if it actually looks like it fits our data roughly. And see, the sampler is going really slow now because it's super wrong. So it's taking a long time, mainly because the priors don't fit the data very well. It'll still run, but it's going to take a little bit longer. Okay, so then we can print our output. And yeah, so not surprisingly, the mean is 5 because we had really strong prior knowledge, and so the data was not able to change that. The prior was so strong that the data wasn't able to overwhelm that. So it's staying at 5, and then the beta is now like 1.43. So to see kind of like how wrong that is, what we can do is we can basically pull out those values and then plot them with the data. So you can see here that this is like the fit from output from our model, and you can see that it's like way totally off from the data because we had these really strong improper priors.
How did you do that?
So I kind of skipped a few steps here, but basically you can extract the posterior samples using this extract function, and that's going to give you 36,000 samples per each parameter. So it's going to give you a big list for each of your betas, and then for your sigma parameter, and then any other parameters. And then I basically just pulled out those betas, and so we can look at what those posterior estimates look like. So these are the posterior samples for the intercept. And so you can see that they're all centered around 5 because we had that really strong prior around 5, and then there's some variability around that. So these are basically the posterior samples that have been summarized. And so we take the average and standard deviation of that to do our inferences. In this case, we just used a really bad prior. But if we use a diffuse prior, things look a lot nicer. So if we go back and run it how we did before, and then we look at that fit.
0.
So your first beta is the intercept,
Mhm.
the second one is the
Slope.
slope, okay.
Yeah. So once this compiles, it'll run really fast, and then we'll see that when we have these diffuse priors, it's going to fit the data really nicely. It's going to look basically, it's going to go completely over that blue line.
You did 0, 100 again?
Yeah, so 0 and 100 again. So these diffuse priors actually informed, that are not informative, they give you proper inference and estimation and stuff. So the priors do matter. I mean, basically, I just wanted to show you that the priors really do matter. If you specify them really strongly, and if they're wrong, then you can have really big issues. But they can ultimately impact your results. They can have a real noticeable impact in your results. This is an extreme case where it was like extremely strong and extremely wrong, but some variations of that can change what your actual outcome is. And then we can also look at these things called trace plots that allow you to look at the chains themselves. So when we talk about the chains, this is what they look like if we plot them out. So on the x-axis are the iterations, the y-axis is the estimate for the parameter. And so the chains start out in all crazy places, and then they eventually converge to a stationary distribution, and they just like happily sample from that until they're done. So this is with the properly specified model. So things look fuzzy and they look nice. So these are the three parameters that we estimated plus this log probability that's estimated, but we're not going to do anything with. So when I say chains, this is what I mean by the chains. They're set, they're like exploring the posterior distribution, and here they're like nice and fuzzy. But sometimes you might get things where like one chain will like go off into the sky, and like that's something that's problematic. But you'll be able to diagnose it looking at these trace plots.
So is each point a mean?
Each point is just an estimate of what that parameter
Okay.
is. So based on the actual probability density, eventually these samples are going to start looking like the distribution that they're being sampled from, if that makes sense. So if it was like just like a population or something, the sample, as the sample gets bigger and bigger, it's eventually going to start taking on the shape and looking like the population that it's being sampled from.
There's two lines here before.
Right, it's so perfectly
but now
fit.
It's so perfect, it's right on top.
It's
of each
exactly,
other.
yeah.
Okay.
Okay, so guys, questions so far? Yeah, Sam.
Could you go back up to your estimates?
Yes.
Looks like your intercept conversion around 0 this time.
Yeah.
So, if I'm interpreting the quantiles correctly, my estimate's at 0.09, and the lowest, it looks like it's basically, if you might say, significantly greater than 0, but then yours...
For this intercept?
Well, yours is negative 0.03, mine's 0.09.
Okay.
So I ran it again, and it gave a different estimate. So it's giving slightly different estimates despite the fact that r hat is 1.
So that means that the chains have converged, but are you sure that the priors are all set the same?
0 and 100. So yours is different from the first time as well, isn't it?
Yeah.
Is it?
Yes.
From the first time I ran it without the different priors?
Yeah, so just if you rerun your script again.
Mine's also different.
Yeah, so that's probably suggesting that we just need to run. I'm trying to keep the number of samples as low as possible so that it'll run faster. If you were going to like actually do inference with this, I would probably increase the number of iterations in the chain to like, I don't know, 3,000 or 4,000.
Or increase the chains.
Or increase the number of chains. So let's rerun this. I mean, I don't think it was that different from what we originally ran, because it's pretty similar to the frequencies estimates. Yeah, negative 0.02 and still 1.18.
Well, it's funny because your trace plot, the lines seem to converge around that negative 0.02.
Mm-hmm.
And you'd think if you ran more samples, it would just keep on converging around that same spot.
Yeah, but I mean, that's why it seems kind of strange that yours is negative 0.09.
Mine's positive 0.09.
Positive 0.09.
Mine's
But
0.02.
it's random data, right?
Oh, right, yeah, exactly. So everybody has a different data set.
Big catch.
Good answer. Thanks, Jim. That makes more sense. Yeah, so the data is randomly generated, so your data and my data are going to be kind of different. But if it's the same data and you keep running them up, that's helpful. But if you have the same data and you keep running the model over and over again, the posterior means should be basically the same. Yeah, so good catch. All right. Okay, so that's kind of like a basic intro to Stan. Anybody else have questions before we move to glmer2stan? Just could be a little bit, the models will be more complex, but the code will be simpler. Nope? Okay, cool. So basically, glmer2stan allows you to write mixed effects formulas like you would for LME4, but then it does all the pain in the ass conversions to Stan. So it writes the Stan code for you. It also converts your data frame into a Stan-friendly list, and then returns what's a Stan mixed effects regression object, which you can do all the stuff that you can do with Stan, but then there's some extra nice stuff because it's a mixed effects model. The other nice thing is that this function computes the WAIS, which is the widely applicable information criterion. This is similar to an AIC or a BIC if you're doing model comparison, but it's a fully Bayesian implementation of that. So you could do something like, is it worthwhile keeping this predictor in? Run it with and without, then compare the WAIS, and if it's smaller, then it's more parsimonious, therefore it's better. So you can use that same logic that you would for frequentist models with this package. So the data that we're going to be using is this sleep study data. It's basically average reaction time per day for over the course of 10 days for subjects in a sleep deprivation study. This is just a standard data set in the LME4 package. And if we run that and take a look at it, basically it looks like this. So we've got reaction time in seconds or milliseconds, then we've got days ranging from 0 to 9, and then you have different subjects. So this is well suited for a mixed effects model because we have days nested within subjects, and then we can look at both random slopes and intercepts. So we can plot those effects first. So if we ignore the fact that the data is nested, we can get our estimates, and basically what that is ordinary least squares fit of this data right here. So here's days, and then here are the points for each participant, but we're ignoring the fact that there's nested data here. So this is just kind of like the very dumb model. It doesn't take into account the fact that there are multiple participants, but we still get an estimate of the line of best fit there. Now, if we take that into account and set random slopes and random intercepts, we can plot that. And basically, this plot is the same data, except the colors now, each color corresponds to a participant, and each participant has their own line. So the mixed effects model is going to be doing this. And the effects that you're going to be seeing, the fixed effects for the slope and intercept, instead of just being the line of best fit, it's going to be the average of all the individual slopes and the average of all the individual intercepts. So the values are going to be the same, but you're going to be able to account for more variance because you're taking into account variance within the subjects in terms of their overall increase in reaction time over time, as well as their relative set point. You just have a faster reaction time than somebody else, and you have your own kind of effect. So that's what's going to be taken into account. And that's not a Bayesian thing, that's just a mixed effects model thing. So if we run it in LME4, we get some output. And so basically the output for our fixed effects is that for every day that goes on, participants slow down by, on average, around 10.5 seconds. Then we also get some random effects output that tells us what our average or the variance for our intercept as well as the variance for the effective days, and then how correlated the intercepts and slopes are. So these are just the actual random effects up here, and we can see that there was 180 observations, but it was nested within 18 participants. And if we compare the two models, the one without the random effects and one with the random effects, the LME4 model fits the data much, much better, which makes sense because we're taking into account the nesting. Okay, so that makes sense? Okay. So basically, glmer2stan is going to allow us to run that same exact model, except all of our output is going to be in terms of Bayesian posterior samples, and we can make the same kind of inferences.
Lower AIC is better? I forget.
Yeah, lower AIC is better. It's like information loss, so you want to minimize information loss. So important annoying fact number 2. Stan does not deal with non-numeric variables. So if you have like a categorical factor, you can't just like feed it into your model like you would normally in R. It needs to be turned into a number of numeric contrast codes, which would be a huge hassle. But one of the benefits of glmer2stan is that it will do all of that conversion and stuff for you. So, but when it comes to those, the index, like the group numbers, that has to be a numeric. So if we had participant IDs like as a categorical like character, like a bunch of observations for Stephanie and then a bunch of observations for Dan, and we just had their names as the identifier, Stan wouldn't know what to do with that. So we need to turn those into numbers. So Stephanie just gets the value of 1 and Dan gets the value of 2. So we're going to do that here and turn that sleep study, that the subject vector, which is here, it's the numbers, but it's like starting from 308 and then goes to 371. But we're going to just turn that into numbers so that it's now just going from 1 to 18. Okay, so this basic stuff, and so here's the actual function glmer2stan, and you'll notice that the code looks exactly the same, pretty much, as the glmer or the lmer function. So reaction is predicted by days plus the random slope of days nested within subjects. The data is still there. Then this extra stuff is whether or not we're going to calculate wastes. We want to, and then the chain diagnostics and stuff, or the chain information. So if you run that, I'm not going to run it because it's going to take like 5 minutes. So I'm not going to do that. But if you print out the output from Stan, you get lots and lots of output because we have lots and lots of parameters.
I couldn't find function glmer2stan.
That's probably because glmer2stan hasn't been libraried. So you have to go back up to the top and library that. But either way, this is the output that we would see from if we had just run this in Stan. Here we've got a beta for days as well as an intercept and sigma, and then we have all of our random slopes and intercepts. So each of these is... So the reason that it takes so long is that Stan has to run every chain for every single one of these parameters. And you have 18 participants, and they each have their own slope and intercept. So all of these are the random slopes and intercepts for each participant, which had 3,600 samples done for them. So that's why this would take like 5 minutes to run. Yeah, Sam.
So we don't have to specify the priors for all this?
That's what we're going to get to. So So glmer2stan writes the Stan code and gives you default super diffuse priors of normal distributions of 0 and 100. The convenience functions that I'm going to show you basically allow you to change the priors, refeed the edited model into glmer2stan and run it again to get output based on whatever informed priors you have.
Okay. And the informed priors would just be the descriptives, basically?
No. So the informed priors would be informed from like an actual previous study or some kind of like actual prior knowledge or some other reasonable prior that you specify. So that's a different kind of question. So unless you have a reason to have strong beliefs about any one of these effects, then you would probably leave it diffuse unless the scale of the data was really bad. But if you like in my dissertation, I ran a sequence of studies. So I used the posterior estimates from study 1 to be the priors of study 2. But if there's if you're replicating a different paper or something like that, you could use their results as informative priors. But you would just have to have a reasonable reason to have those beliefs, I guess, or justify them.
So hypothetically, if you saw one participant and you knew them and they were a genius, you could set their prior to be a certain thing based on your knowledge of them?
Probably. There's probably some way to do it. I won't be describing a way to do that in particular because that would be like a random effect. So I don't know how you would specify a random effect for one participant, but it would probably be somewhere in the covariance matrix of slopes and intercepts per participant. There's probably a way more complex than we'll go over today.
Thanks.
Okay, so this is the generic stan output. It's really messy because there's a lot of it. But we can clean it up using the stanmer function that looks a little bit more like the output from LME4. So we get our estimates, which, if you guys remember, basically we're getting the same estimates from the Bayesian and the frequentist models in terms of what that expected value would be for the slope of days as well as that intercept, as well as the intercept. Then we have our standard deviation and correlations. So again, the slopes and intercepts are not highly correlated. This is just replicating the output from the LME4, but it's being informed from this Bayesian process. There's also kind of a default plot to look at the effects, but it kind of looks awful. As you can see, it's like really ugly and doesn't make sense. So, yeah. But we can also look at these trace plots. So here are the chains for each of the different parameters that we were interested in. So there's lots of them because there was lots of parameters. So these are all for the slopes and intercepts. So we can do some diagnostics here and see, like, are the chains sufficiently fuzzy? Is something going off weird? Did one of the chains like randomly die because it got stuck somewhere in a local minimum? All those things can be problematic, but you can diagnose them visually.
When that happens, what do you have to do? So if the chain goes off to like Netherlands, just rerun it, or?
I mean, it could be that there's a problem with your data. Like, there's there could be lots of reasons for that. So you would look at your data. I mean, you could rerun the chains longer or something, but or your priors are poorly specified. There could be lots of reasons that something like that could happen. But the important thing is that you notice it, because the output itself won't necessarily like give you a warning that like there's a weird chain.
And just to be clear, these are estimating the slopes and intercepts for each person.
They're estimating the fixed effects, which is the overall slope and intercept, and then estimating individual slopes and intercepts, which we'll kind of show in a second. You can also run this with just random intercepts, which converges much faster. So let me see if that goes faster. So here, I took out the nesting of days and just put an intercept there. So it's basically saying that the intercept for each participant changes, but the slope, the effect of days is the same for each participant. So that'll compile and then run fairly quickly, whereas the other model would have taken like 5 minutes to run because you're estimating like 60 parameters. So while that's kind of doing its thing, it's like making sense. I don't know. Is this like total waste?
It's really good.
Okay. So there it's going just fine. Again, it's just sampling to the chain. So basically just what you're seeing visually in the trace plots is what's actually happening right now in the background as the chains are exploring the parameter space.
Can you turn that off?
This output off? Yeah. There's some arguments in glmer2stan that you can set it to just tell you if a chain is done or just not tell you anything. But this is just the default at 10% increments. So you can look at the model here. So the output from glmer2stan is this S4 class of object, which means that it has a ton of stuff in it that can be subset with this at function or this at separator. So you can look at the stan model. So this is the model code that glmer2stan wrote for us. So this saved us a lot of time because now we don't have to learn stan code. So it wrote the data block for reaction days, subject index, the number of subjects, transforms the data, sets up all the parameters, and then here it gives us our nice diffuse priors. And then the reason that things take a long time is that there's a for loop where basically everything is nested within this for loop because it's doing the intercept and slope fitting process for each participant. So you can see like for j in 1, 2, the number of subjects, it's going to run this procedure multiple times. Yeah.
So this is where if you had like a prior for individual, you'd have to just write out. You'd have to do like the for loop and just manually set them.
I really don't know exactly how you go about doing that because I don't know where the priors, because for the random effects they're not they're set as like just a matrix of correlations. between intercepts and slopes for each participant. So you'd have to go in, and I don't know where that's being represented here.
Okay.
But again, this code is not perfect stand code. It's just stand code that runs. But there's probably a way that you could write custom stand code that would allow you to do something like that. But the glmer2stan function doesn't really bother itself with setting specific priors per participant, but you could do that probably.
Okay.
Yeah, I mean, in that loop there, rather than doing a loop, if you wanted to specify some prior for a particular I mean, that sets up the model for each and fits it for each subject. True, yeah.
Pretty much, yeah. So I think this multi-normal, this is a stand function. I think that's setting up a multivariate normal distribution with zeros for the subjects and then some variances for the subjects. So,
I mean,
yeah,
I think it'd be not advisable to
it would probably not be a trivial
set
thing to
prior.
do.
Oh yeah, and
But,
I'm just
yeah.
kind of curious.
Yeah. Okay. So glmer2stan is nice too because you can turn the sampling part off, and then you can just get the compiled model and the data and the Stan-friendly data object. So if you wanted to do stuff in Stan, you could just use glmer2stan to do the annoying parts of writing Stan code and making the model and making the data a list by just turning sampling off. So what I've done here, this is the same exact code, except I just added this argument, sample equals false. And so now we've got a list. So now that outputs a list that has the data in it, as well as a character string of the model, some initial estimate, or some the initial values for the chains, and some other random stuff. But so like here's the data that I didn't have to translate. I didn't make this list, but glmer2stan made this list. So it gave me an object, or it gave me a scalar for the number of observations, 180. Then I have the actual data vectors, then the subject indexes, and then the variance or the covariance matrix for the subject intercepts and slopes. So all that was done not by me, but by glmer2stan, which is nice. And then we can output the model. And now what we can do, if the model is really long and it's like a pain to copy and paste it from the console, you can use this sync function, which basically writes output to a text file, and then you can manipulate it in there. But yeah, so that kind of gets me to like my own function, which is just a tweaked version of my glmer2stan, that basically fixes a bug when you're writing formulas that have lots of high-level interactions that are specified with a colon instead of an asterisk. For some weird reason, it gets mad and it kills the random effects and doesn't tell you. So I had some very weird results for my dissertation until I noticed this. But more importantly, it allows you to feed in your homebrewed model into glmer2stan and then run that. So basically, the idea is you run the model with no samples, then you copy and paste the Stan model, change the priors, and then refeed that text, that piece of text into glmer2stan, and then run it based on your model, which has updated priors. So that's like the main enhancement that you get with this function that you won't get with the standard glmer2stan function. Does that make sense?
So you can set your priors?
Yes.
Okay. Yeah.
So you can't set priors in glmer2stan by default.
Right.
You can output the code and then run it in Stan, but then you have to like format your data objects and do all the annoying stuff. So basically, I cut out that whole process by just allowing you to feed your edited model back into Stan.
Nice.
So does that like logic make sense?
Yeah.
So so we've got my glmer2stan. Again, this is just the same output, the same model. So basically, my function does the exact same thing as glmer2stan when you set this my model argument to null. So if you leave it blank, it just does whatever it would normally do, set diffuse priors. But if you change it and specify a specific object, it'll use that object as the model and run it based off of that model.
So the idea is you output stand code, save the stand code as an object, and then you put that object's name into that model.
Exactly.
Okay, cool.
Yeah, so that's basically what I did. So I took out the model from no samples. So I took out that stand model that glmer2stan wrote for me, and then here it is in text form right here, and I'm saving it all to m2g2s priors. That's the name of the object. So this is all the same. Boom, an informed prior. Look at that. So I just wrote this in. I don't have any reason to believe this. I just gave it a strong prior that is also going to work because I know the effect is right around 10. So I'm basically saying that my prior beliefs of the beta 4 days of that fixed effect is a normal distribution centered around 10 with a standard deviation of 2. So pretty strongly informed. If you were going to do something like that, you'd have to justify it somehow.
Yeah, you wouldn't run an uninformative prior to find out what the
Right, that would, yeah, that's...
posterior estimate is, feed that back in as an informed prior, and then...
Yes, exactly, yeah. So that would be like...
Total reach around.
Yes, that would be bad.
What
So-
a route.
Yeah. So yeah, that would be super bad. You can't just like use your posteriors to become your new priors and then rerun that to have like a perfectly fitting model that fits a bunch of noise and stuff. But if you did have a reason to have strong beliefs about a parameter, you could input that here, and then you just I'm just editing this as text. So that all is the same, and then I have rerun it with m2g2s prior specified as the model. So yeah. So then we get some output, and the output looks roughly the same, but what you'll notice is that the waist, that model fit diagnostic, is 1717 with the priors, which are cheating priors, but without the cheating priors, it's 1720. So basically, we've made the model fit better by using this informed prior. If this prior was informed with actual knowledge, that would be a good thing, but since I obviously just like made that up, it's less meaningful. But if I had like run a previous study that showed that maybe a pilot study with like a couple of participants that showed that slope was around 10, I used that to inform my priors. I actually gained something by using that prior knowledge. In particular, I have a model that fits the data better.
So we'll just say, in study 1, you have like the means, like the estimate and the standard deviation variability around that estimate. You just copy and paste that in, or would you make it less?
Yes,
certain?
yeah,
What do you inflate the uncertainty?
So you could. I mean, there's different ways you could go about
Yeah.
doing it. If like you think this other study is maybe slightly different, but it might be centered around the same. It might be in the same neighborhood. You could maybe double or triple the standard deviation, but keep the center point
The
of that
estimate.
distribution the same.
Okay.
I mean, if it was like 50 subjects, you might, in one study, you might, inflate the uncertainty considerably.
A little
But
bit,
if it
yeah.
was like 10,000 subjects and 5 previous replications of that, you might
Make it
make it close to some,
Okay.
meta-analysis of that
Right.
effect. So
I guess it kind of depends on what reviewers would take.
a little bit, yeah.
Yeah.
Also, what you believe.
Okay.
Yeah. So the priors. I mean, there's nothing that's stopping you from putting whatever you want in there. But if you're gonna you have to say what they are eventually when you write up your results. So you have to defend it to someone. So the nice thing is, I mean, if we're running this as a frequentist model, we get the same fixed effects estimates. We get, and we also get estimates for each individual slope and intercept. The one thing that we don't, but we only get one value for each person. Each of these effects only has just one maximum likelihood estimate. So the nice thing is that in addition to setting priors, we can also look at what are other believable values for our parameter estimates and how they fit the data. So we can do posterior predictive checks where we're basically saying, like, what are some, so I know what the best fit line is, but what are some other potential lines that fit the data also maybe reasonably well, other believable values for our parameter estimates. That's something that you couldn't do in a frequentist model because you get one estimate. So we can look at how our model fit overall. Let me do that. Okay. So the red line is the model fit from Stan, and the blue line is just the least squares fit. So this is just kind of an overall general predictive fit, like it fit the data pretty reasonably well. It's not something weird or crazy or all over the place. It seems to fit the data well. And the nice thing that we can do is we can now look at individual slopes and intercepts. So we're going to break out this plot here into each individual slope and intercept effect, and then we get believable slopes and intercepts for each participant. So I'm going to skip over some code that gets us to that point, just so we can look at the plot, which is kind of cool. So here we have our 18 subjects. Their data points are just the big red diamonds so that they're easier to see. And the blue line is their least squares fit. And then the black lines are 20 credible regression lines based on our analysis. So you can see that some participants are like wonkier than others. Some have like no effect of sleep deprivation. Some have a really strong effect. But they're not totally consistent. Some have these weird outliers and stuff. So basically what this output is credible regression lines and intercepts for each of our different participants. So and like a different way to visualize our random effects in a way that we wouldn't be able to do with LME4.
The diamonds are what again? The raw data?
Yeah, they're just the data points, but I made them bigger and redder so that you can see them. And to do that, basically what I did is all of those posterior sample estimates are available in the in the samples, in the output of the samples, where if I use this extract function, basically it gives me this gigantic list of all the parameter estimates for each fixed effect and each random effect, so a very, very big list. Then I can basically just take random samples for those specific parameters, and this is kind of more complicated. This is more like an R code thing than a Bayesian thing, but it's there so you can kind of explore it. Basically trying to figure out where are the correct samples and then pull some credible posterior estimates for the slope and intercept for each participant, put it all together in a big data frame, and then put it in a plotting function. So any questions so far on the my GLME rstan? So like refeeding the priors into the model, or changing the code and then refeeding it into the model. Yeah, Sam.
So it gives you the most credible estimate, and then it'll give you some alternative estimates. And that last thing you said is essentially like you're resampling from that whole list of alternative estimates. So
Yes.
Is it a less reliable estimate?
So what you're getting for each parameter, you're getting, in this case, you're getting 36,000 samples, 36,000 believable values for your, let's say, for your specific intercept, right? Like just for your random intercept. So the mean of those 3,600 samples is going to be the same probably as the fixed effect, or as the LMER estimate. So that's your best guess. The mean of all those samples, that was the most like frequent value, sort of. But what you can do is you have like your one best guess, but then you also have other reasonable guesses around that guess, right? Because it's not necessarily perfect, so you're looking at other potentially believable regression lines that are slightly different from the best guess, but are still believable. Does that make some sense?
Yeah.
So it's not necessarily going to change your inferences. It's not going to say like, oh, this is significant versus not significant, but it would allow you to, diagnose if there was weird issues in the data, or it just gives you a richer set of inferences that you can make. It's not going to change whether a parameter is significant or not. It just gives you more freedom to explore your actual output. Any other questions or anything? Okay. So I have some other functions that are also on the GitHub site. one of them is specific towards making inferences. Basically, you run a regression, which predictors were significant, which ones weren't. How do you decide what that is? So in a frequentist model, you get a p-value, and if the p-value is less than some criterion, it's significant. You get stars, which make everybody really happy. The Bayesian output doesn't give you stars. It doesn't have any significance testing built into it. So you basically two things that you can do, and you can come up with your own methods for determining significance based on your own criteria. But one is this thing called the region of practical equivalence. So for like a beta coefficient, a null value would be 0. Like there's 0 relationship between this predictor and the outcome variable. What you can do is you can define a region of practical equivalence of values that are similar to the null value that are also really small and equally meaningless. Because in reality, most relationships are not perfectly 0, but somewhere in the neighborhood of 0 with some jitter around that. So basically define a jitter region and then figure out how many of your posterior samples for that parameter fall within that region of practical equivalence. And then if that's less than, say, 5%, then lo and behold, you have significance. So similar kind of idea, but just you have to do. But this function kind of does a little bit of that work. So this prop and rope function, basically you set the minimum and maximum for that region of practical equivalence, and that's going to depend based on the scale of your parameter and whatever other information you might have that would define a region of practical equivalence to the null value. So here, basically saying that anything that is negative 1 millisecond or positive 1 millisecond around 0 is going to be considered practically equivalent to 0. That's like a meaningless effect of days. So what this is going to do, it's going to compute the proportion of the posterior sample estimates for the fixed effect of days that fell within that negative 1 to 1, and 0% fell in there. It was a pretty strong effect. So that is one criteria for rejecting or for identifying significance. Then I also have this function, my posterior plot, that kind of visualizes this whole process. If you have a model with lots of predictors in it, you want to determine which ones are significant, which ones weren't. You don't want to compare the numbers in the table output. This my posterior plot basically visualizes the region of practical equivalence and the 95% HDIs for each of your different parameters. So what I've done is I've added some complexity into the model by just making a new variable called days2 and threw that in there. Hopefully it's there. Oh, okay, it's got to run. All right, so the more complex model is going to run, and then we'll have lots of fixed effects parameters, which we can then visualize as how much of them fall within that region of practical equivalence, and exactly like where those HDIs lie in relation to the null as well as to the other parameters themselves, which will make more sense once the figure is actually up.
Do you set the region of practical equivalence the same way that you might set the priors? So
yeah, I would say that.
stuff?
Yeah, I don't know. Jim, do you have any experience with like picking a rope, a region of practical equivalence?
Not
Whatever.
really a rule. It's more or less common sense, I think, is what I would say. Isn't that
Just
what
tiny values
small
around
values,
0.
Yeah. I mean, if, I don't know, like 1% either side might seem reasonable. But I mean, if your scale isn't on 1% increments, then you might have one increment either side of 0 might work.
Yeah, like so for this example, I set the rope to be -1 and 1. But if this was scaled data, then 1 would be basically that would be a huge effect. That would basically mean a 1 standard deviation increase in days would be a 1 SD increase in reaction time, which would actually be a large effect. But since it's in the scale of seconds, it's in the scale of milliseconds, 1 millisecond is not very meaningful. So, I mean, if you were to come up with conventions, I would guess it would have to be relative to some scaled data, because betas are interpretable regardless of the scale of the raw data. So for my dissertation, I set the rope to be 0.05. So 5% of a standard deviation was like what I considered a nuisance effect. And so my rope was defined around those values. Has people that have the like code and stuff, has that been running okay? None of it's been running?
I stopped trying.
Okay.
I saw what I wanted.
That's fine. I mean, it takes a long time, but if you have the software and stuff installed, you can play around with it.
Have you found any other benefits from Bayesian approach? Maybe that formed dissertation a different way, and if you didn't use it?
Yeah, I mean, I would have gotten different results if I had used a frequentist model because I actually used informed priors, and in particular, the priors are helpful if you have like multicollinearity, which I did because I had lots of high-level interactions. So the low-level effects are interacting with the high-level effects, but by setting the priors to be a little bit more informed for the effects that I knew about, it helped basically reduce the effect of that multicollinearity had on suppressing my results.
Okay.
So
you're just able to model it better because you did an earlier study, you figured out the multicollinearity issue, then you set the priors for like a second.
Yeah, so like limiting the number of believable values. How did I do that? Oh. Yeah, so kind of restricting the range of believable values for the parameters I knew about basically helped protect that effect from being suppressed by multicollinearity with higher order effects.
Okay.
Like cognitive flexibility predicting change blindness was my one effect that I knew a lot about as a main effect, but then there was also these high-level interactions, and because they're correlated, it would make my main effect of cognitive flexibility appear smaller than it actually was. But by using an informed prior, it basically protected that main effect from suppression of higher-level interaction.
So was it either that the prior made your effect bigger, which is more robust against the collinearity, or did you model the collinearity that made it stronger?
No, I didn't model I just
Okay.
modeled the main effect, and
Okay.
it didn't change the magnitude of the effect, but changed the range of the believable values. So yeah, with that multicollinearity is just going to make the HDI a lot bigger and make it harder to determine whether or not it's significant. But if you use informed prior knowledge, you're going to limit the amount that multicollinearity is going to expand the HDI.
Because it's starting to make a lower point.
Yes,
So
exactly.
pretty much you're saying that if you have informed priors, you can lower your uncertainty around your values.
Exactly, which
And
you,
that's like-
by definition,
that's-
is what you're doing.
And that's like increasing power. Okay.
Yeah.
Because like a frequentist approach is like even if you know better, just kind of like a shotgun approach, which is like a huge spread.
Right. So even if you know better, your model doesn't know that you know better, and so it
Okay.
won't do anything. Yeah.
So the glmer2stan,
Yeah.
that's not for like a logistic dependent, right?
Yeah, you can use it for a logistic dependent
can?
variable. Yeah.
Okay.
It has all the functionality of the LMER package in terms of modeling distributions.
Do you have to set it to logit or whatever? Or
Yeah, you need to set the family
formula,
to
the
be
family to,
logit or whatever it is.
I think it's logit. Oh yeah, you're right. It's fine.
Yeah. So so we had 3 fixed effects in this model. I made a new variable called days2, and then I had to interact with days. It's just noise, so it's not going to be a significant predictor. But here the days effect is represented here. And so this posterior plot basically just visualizes the stan output, where these bars are corresponding to the 95% highest density interval. Here's the null value 0, the region of practical equivalence, -1 and 1. And then they turn blue when there are less than 5% samples in the region of practical equivalence, and then you just like eyeball to see whether it crosses 0. So those are kind of the two, when I ran my dissertation, those are the 2 criteria I used. The 95% HDI can't cross 0, and you need to have less than 5% of your samples in the region of practical equivalence. You could probably not do that and be fine, but that's just what I did. So these functions are set with that criteria in mind as default, but then those can all be changed.
So the first one's the credible or high density interval. That's kind of what frequentist people do in general. Then the second one you said, what was it? The 5% rule. That's
Yeah.
uniquely Bayesian.
So the frequentist equivalent would be a confidence interval, 95%
Right.
confidence interval. But you can't interpret that the same way as a Bayesian HDI because this is a range of credible values, but the confidence interval is just a range of values that would have rejected the null if you ran this study like a million times. Yeah, an infinite number of times. So they can't be interpreted the same way. So this is totally different. I mean, in a way, this is totally different, but also similar to how you would interpret a confidence interval if it crosses zero.
You can interpret these how people intuitively interpret confidence intervals, but shouldn't actually interpret
Okay.
it.
Right.
So, for instance, it's a distribution within that. So, values have probabilities within that range. So, if they're closer to one tail, then they're less probable one.
Mhm.
If they're closer to the other, they're more probable. Whereas confidence intervals, they're all the same.
So you're like, so that's the 95% marker for all models. So like each point could be a parameter model.
This is just for one specific parameter.
Right.
So you can imagine.
Right, all parameters.
Yeah, so you can imagine that like there's like a little normal distribution over each of these little things. Right, so the dot is the mean of that normal distribution, and then this just marks off the top and bottom 2.5%. So, and then in rstan, it actually shows you that kind of like kernel density output. But basically, this is a graphical visualization of the table output, and it's especially helpful if you have like, I don't know, 15 parameters, 15 fixed effects or something. You can get like a whole bunch of these, and you can see which ones are significant because they're blue, and you can see where, you know, the magnitude of the effect and how much uncertainty there is around that effect.
Is the distribution of parameters always going to be normal?
No, but the way that we're modeling it as regression coefficients, we're modeling them as normally distributed. So our priors are normal, and we're assuming that we're basically making an assumption that the betas are going to be normally distributed. But if you had a different kind of model, then and you're modeling something that's not a regression coefficient, you might have a totally different distribution. But for most inferential stuff, I mean, if you're comfortable with using linear mixed effects, that covers most of the inference you would want to make from experimental, you know, data, where you can do any categorical comparisons, any continuous variables dealing with any nesting or slope coefficients, any of that stuff you can do with LMER, and now you can do it in a Bayesian framework, like I would say like maximum complexity that most of us would deal with within a particular data set. Because we usually work in this like GLM framework where even when we're like super complex, we're still just modeling like beta coefficients and linear rectilinear effects.
It doesn't do non-linear models.
Right, yeah, so that's the other thing. So LMER doesn't really do nonlinear models, and so glmer2stan doesn't really do nonlinear models either.
Do you know if Stan?
Stan definitely can. It's just you'd have to write the Stan code, which would be annoying.
So at least with this, it makes it easier to learn Stan code.
Yes.
Because
you can edit it. Yeah, it'll write it. It'll write something that runs, and then you can edit it and see, you know, where it breaks, where it doesn't break. Yeah, so that pretty much covers most of the functions that I wanted. I mean, I know we've been going for like almost like 2 hours now, so I don't want to like go forever. But that covers most of the functions that I wanted to like show you guys. And I mean, functionality-wise, interpretation-wise, the figures and graphics in terms of how you can make the output more interpretable, how you can change the priors, how changing the priors has a measurable effect on your actual outcome. And the last thing is this rstan package, which basically launches an interactive web app that allows you to explore all these parameters. So this is kind of a similar plot to what I was just showing you, except it is for all the effects, and then you can like specify which ones you want. So you can look at just like the intercept and days and like days 2 or something.
Can you export those plots in an editable form?
You can save it as a ggplot object and then edit it from there. You can also get those kernel density estimates, so you can actually see the normal distributions of each of the posterior sample estimates. You can also color the points by the convergence statistic, which is just, again, another cool way to look at your, make sure that your results are making sense. Then everything can be saved to a ggplot object. You can change the credible intervals. Then you can get the table in this nice format. And this kind of looks bad, but you can control what is visible in the table, and then you can save it as a data frame, or you can export it to a LaTeX object, and then it would give you a LaTeX table that looks like this, but formatted in LaTeX that you could like paste into a document. The coolest stuff I'd say is like the diagnostics, though. In particular, for looking at like interactive trace plots. So these are like the trace plots we were seeing before, but you can actually control the number of iterations. You can specify which parameter you want to look for, like this intercept, and explore these different relationships. So this is for the intercept, and then you can look at density, autocorrelation, and all that stuff for a particular parameter, like for days, for like a fixed effect that you care about. Like autocorrelation, lag, the density of the estimate, all of that stuff. So it's cool, it's a good learning tool, and it's also good for diagnosing really if you have complex models and stuff. There's also like dynamic traces where you can like zoom in on a particular aspect of the sampling. So this is like, just like 10 steps or something. If you have like a dead chain or something, this would be useful to explore, like where did it break and why, or try and figure that out. So this is just a cool tool, not necessary for inference, but good for learning and diagnosing weird stuff. So yeah, that pretty much covers everything I wanted to talk about. Do you guys have like other questions, or if you have your own data that you wanted to like submit to some of this crazy stuff, you could like do that?
So I'm trying to get my own data to work, and it's taking forever, and I think it might be a problem.
Do you have random slopes and intercepts?
Yeah,
How many data points? How many subjects?
84.
Yeah, that'll be a while.
Couple of hours probably.
But it says
Probably be.
So I did glmer2stan,
Mm-hmm.
and then I specified logit
Uh-huh.
for the family. That's right?
Depending on what glmer2stan calls logit, then it could be right.
And then it seems to be running, but then it says the current Metropolis proposal is about to be rejected because of the following.
Does it say it over and over and over again? Is it just like a block of red?
Yeah, it's like a block of red, and then for each sampling step, it gives me this block of red.
Yeah, that sometimes happens when you have a lot of parameters, because you have 84 subjects, so you have 84 by 2
And then
plus the
there's-
fixed effects.
And then, yeah, plus the fixed effects.
Yeah, so you just have like a shitload of parameters, which is going to make it really difficult for that to
So-
work. I mean, it'll still give you output.
But can I trust the output?
I would wait and explore it, look at the trace plots and see like what it looks like. I mean, that's the nice thing, is that like it will give you trouble, but then you can actually diagnose what the problem is, as opposed to just like fail to converge.
And then if you find the problem, like how would you fix it?
I don't know. There's different things you could explore. Depends on what the problem is.
Right.
But you just have a really super complex model. So I don't know. You might want to group your participants differently or something.
Uh-huh.
There's different ways you could approach it.
So it's not doing it for every iteration, so.
Yeah, that I've seen that error get thrown when you have a super complex model with lots of parameters.
Okay.
Are there any requirements, like number of observations you have to have before this will work?
No, the Bayesian model will run, and it's actually nice if you have few observations and strong prior knowledge, then that's a good thing. So like, let's say you run like 2 like big studies with like 200 people, and then you run like a pilot study with 30 people. You can use the posteriors from those first 2 studies to basically beef up the inference that you would get from those 30 people. Because if you're just replicating these 2 other studies, you get to leverage your prior knowledge, and you get much better estimates much quicker based on that.
And I believe too, can you run a Bayesian analysis with just one observation?
I mean, it would depend
I've heard
on.
you can do that. Like,
Yeah, I mean, you could, because you would just update your beta
Yeah.
with one data point,
Or
so
just
it'll
like-
look like your prior, basically.
Like any frequentist model, it's impossible.
Yeah, I mean, you could to see how much the posterior changes.
Right.
Because, yeah, now probably if your posterior is, sorry, if your prior is reasonably narrow,